Hi, everyone. Remember in the last mini lecture, we talked about Sommerfeld theory. Remember that this is essentially the Drude model plus Fermi-Dirac statistics. We talked about some basics of how Sommerfeld theory works. In this mini lecture, we're going to compute the ground state properties of the free electron gas. So let's start by computing the ground state energy. Of the free electron system in the Sommerfeld model. So let's call that capital E. That's different from curly E, which is the energy per particle. Here, capital E will be the total energy of the system. So this will be twice times the sum of all k values with magnitude less than kf of h bar squared over 2m times k squared. The factor of 2 here occurs because we can put spin up and spin down electrons in each level, one spin up and one spin down electron in each level. All right, so let's use our state counting strategy. We want to compute some quantity, which is the sum over some values of k of some function f of k. Well, let me multiply and divide by the volume per point in k space. So let me indicate the volume in k space as delta k here. So you see here I've multiplied by it, here I've divided by it. Now, notice that the size of delta k goes to 0 as the sample volume goes to infinity. So we can write the limit as v goes to infinity of 1 over v times the sum of all values of f of k as the integral dk over 8 pi cubed of this function f of k. So if you like, we've shown how using our state counting strategy, how by using our knowledge of the volume per point in k space, we can easily compute quantities per unit volume as integrals of functions of k. So maybe one thing to note is we can't really take the limit of v going to infinity in practice, but we'll typically assume that our calculations apply to very large but finite objects, and because they're so large, we'll assume that this bottom expression is true to a very high degree. So let's start by computing the energy per unit volume of the free electron gas in the Sommerfeld model. So this is 1 over 4 pi cubed, if you like, 2 over 8 pi cubed. Again, the factor of 2 comes from spin degeneracy. Now here's our integral. We're going to integrate over all values of k less than kf. We're going to integrate inside the Fermi sphere of dk times h bar squared over h bar squared k squared over 2m. So doing some algebra, this is h bar squared over 8m pi cubed, 0 to kf, dk times k squared. So if you like, I've implicitly written this next integral in spherical coordinates. I've written the integrand as going from 0 to kf to integrate that. We're going to integrate over all of the angular variables, and we're going to only take the radial variable from 0 to kf. So now let me explicitly do the angular integrals, there's no angular dependence here, so the theta and phi integrals just give us a factor of 4 pi. Here's now the radial integral. This is no longer a vector dk, but a scalar. The dk, if you like, the dk times k squared came from the volume element over here. This is now an integral that's easy for us to do. This is h bar squared kf to the 5th power over 10m pi squared. So this is the total energy per unit volume of the free electron gas. Now the energy per particle is equal to the energy per volume, which we just computed, times volume per particle. It's E over V times 1 over the density. Remember that we derived in the last mini lecture that the density is kf cubed divided by 3 pi squared. So using our result for the total energy per volume, as well as our previous result for the density in terms of the Fermi wave vector, we have that the energy per particle is h bar squared kf to the 5th power divided by 10 m pi squared times 3 pi squared over kf cubed. This is 3/10 h bar squared kf squared over m, which is 3/5 of the Fermi energy. If you like, this is 3/5 times kb tf. Now this is a little bit surprising because we're computing the average energy per particle at t equals 0 in the ground state. And you see that it's a significant fraction of the Fermi energy. You remember that TF is of order 10 to the 4 degrees Kelvin. So this is indeed a rather significant energy for t equals 0. This is a direct consequence of the Pauli exclusion principle, which forces electrons to occupy higher energy states, even in the ground state. So contrast this with the classical value. Where the average energy per particle, if we assume equipartition, is 3/2 kBt. So this is of order 10 to the 2 Kelvin at room temperature. This is of order, well, so the energy is equal to kB times 10 to the 2 Kelvin. Here the energy is equal to kB times 10 to the 4 Kelvin. So the average energy per particle in the Sommerfeld model is vastly larger than the average energy per particle in the Drude model. Let's compute the pressure associated with the free electron gas at t equals 0. So that is minus dE dV at constant particle number. Remember that the energy is 3/5 times the total number of particles times Fermi energy EF. This is 3/5 and h bar squared over 2m n over 3 pi squared to the 2/3 power. So you see that the pressure therefore must be equal to 2/3 E over V. Why is that the case? Well, you can see that the density is proportional to 1 over the total volume V. And because the energy is proportional to the density to the 2/3 power, you see that it's proportional to V to the minus 2/3 power. So taking a derivative with respect to V of something that is proportional to V to the minus 2/3 power will bring out a factor of 2/3 and 1 power of V in the denominator. All right, so stick with me here. We can also compute the bulk modulus. This is the stiffness of the material. So we'll say B is equal to 1 over K, where K is the compressibility. B is the bulk modulus. So B, which is 1 over K, is minus V times dP dV. Well, we just saw that the energy was proportional to V to the minus 2/3 power. This means that the pressure is proportional to V to the minus 5/3 power. So this means that the bulk modulus is 5/3 of the pressure, which is, somehow this just erased here. Can I bring it back? Nope. Let me recap. The energy is V to the minus 2/3 power. The pressure is proportional to V to the minus 5/3 power. So the bulk modulus, which is minus V dP dV, is going to be equal to 5/3 of the pressure, which is 10/9 of the energy per unit volume, which is 2/3 times the density times the Fermi energy. Now, why am I telling you all of this? First of all, there's a well-defined prediction for what the bulk modulus of a free electron gas at T equals 0 is. This is almost entirely a result of the Pauli exclusion principle in Fermi-Dirac statistics. You can compute what this is. Indeed, you find that this is actually on the same order as the compressibility or bulk modulus that you measure in a real metal. So what this means is that the stiffness of ordinary materials has a non-zero contribution from the Pauli exclusion principle. It has a non-zero contribution coming from the fact that no two electrons can have the same quantum number. So this is actually an experimentally measurable and relevant quantity, and it's one of the perhaps most important and interesting ways in which quantum mechanics impinges on everyday life. So the next mini lecture will start to consider what happens when T is greater than 0. We'll start by refreshing ourselves, refreshing our memories on how we think about the Fermi-Dirac distribution and what its implications are.